Hello and welcome to this video on aldol reaction and aldol condensation. Aldol reaction was first discovered independently by Adolphe Woods and Alexander Borodin in 1872. Now, aldol reaction is about the formation of aldol, a compound that contains an aldehyde part and an alcohol part. In an aldol reaction, we get what is called as a beta hydroxy carbonyl compound. Let's understand what that is. Suppose we have an aldehyde here. This is the aldehyde part. And on the beta carbon, that means this is the functional group. This is the alpha carbon. This is the beta carbon. And you have a OH here. So you have a beta hydroxyaldehyde. This is known as the aldol. It contains the aldehyde part and the alcohol part. So we are going to talk about the formation of this compound. And here the reaction combines two carbonyl compounds, and the original experiment used the aldehydes to form a beta hydroxy carbonyl compound in the presence of dilute base or acid. Now this reaction is called aldol reaction because the product of the reaction of 2 mole of an aldehyde is an aldol, aldehyde and alcohol. Now, if this beta hydroxy compound, for example, let's look at this one. This is the beta hydroxyaldehyde. Now, if the alpha carbon contains an H here, then we can remove this OH and this H by heating this. And we get an alpha beta unsaturated aldehyde. So apart from getting the aldol, which is this product, this can be heated to yield an alpha beta unsaturated. This is unsaturated aldehyde. So this can also be produced in this reaction. So if the beta hydroxy carbonyl compound is further dehydrated, we get what is known as an aldol condensation. That means the formation of beta hydroxy carbonyl compound is called aldol reaction, and the formation of the enol or the enone, which is the unsaturated alpha beta unsaturated aldehyde or ketone, is called aldol condensation. As we would know, condensation is a reaction in which two compounds combine with each other, they condense with the removal of one molecule, and generally that molecule is water. So when the aldol is dehydrated, a molecule of water is removed, and the total reaction is then called the aldol condensation. The advantage of because the addition is reversible, good yields of addition products are obtained only if it is removed. That means the formation of the beta hydroxy carbonyl compound is a reversible process. So that if you want to make it irreversible, you got to keep removing it from the reaction mixture. And the other option is you can dehydrate it to form the enol and the enone, which will help in making sure that the reaction becomes irreversible. So that is another way of making the reaction irreversible. The advantage of aldol condensation over the aldol reaction is the irreversibility of aldol condensation. So let's understand what is this aldol condensation and aldol reaction. Now, the first criteria for an aldol reaction to happen is that we must have an aldehyde, preferably an aldehyde. You could even have a ketone. So you can have an aldehyde or you can have a ketone. And the other important criteria is it must have alpha hydrogens. Now, this is the functional group. The carbon attached to this functional group of the aldehyde is called the alpha carbon. The hydrogens that are attached to this alpha carbon are called alpha hydrogens. For aldol reaction to happen, alpha hydrogens are required. If it has only one alpha hydrogen, then it will stop at aldol reaction. If it has more than one alpha hydrogen, then you can even get aldol condensation in the product, and that you will understand when we see the reaction. So let's see the reaction. Aldol reaction, as we said, requires the presence of alpha hydrogen. So this is the compound. I'm taking 2 mole of acetaldehyde. It contains 3 alpha hydrogens, as you can see. Treated with a dilute base, the reaction is reversible, and we get a beta hydroxyaldehyde. And then this will undergo dehydration. This OH will go away, one of the hydrogens will go away, and this is irreversible. And we get alpha. This is alpha carbon, this is the beta carbon, alpha beta unsaturated aldehyde. So this is the overall aldol reaction. Up to this stage, it is aldol reaction, and when it yields this product, it is aldol condensation. Now, it is always noticed that the aldol reaction is more favorable for aldehydes than for ketones because of more acidic H and more electrophilic carbon. For example, if I take an aldehyde like acetaldehyde, and if I compare this with acetone, both of them have alpha hydrogens. We will notice this hydrogen is more acidic than this hydrogen. That is because this alkyl group exerts a plus I effect, and any kind of a releasing effect will decrease acidic strength of these hydrogens. Therefore, the alpha hydrogen of aldehyde is more acidic than the alpha hydrogen of ketone. So that makes it easier for us to do aldol reaction here than in the ketone. The second reason is this carbon, the carbonyl carbon, is more electrophilic in the case of aldehyde. More electrophilic meaning this contains greater positive charge. Again, for the same reason, there's an alkyl group here, and this alkyl group exerts a plus I effect, and the plus I effect diminishes the electrophilic nature of this carbon. So aldehyde have more electrophilic carbonyl carbon than ketone, and both of these two are important for aldol reaction and condensation. So the aldol reaction is more favorable for aldehydes than for ketones because of more acidic alpha H and the more electrophilic carbon. Now, in case the aldol product contains an aryl group or a phenyl group in the beta position, the dehydration occurs under the conditions in which the aldol addition is carried out. That means we don't need additional heating. So here the product is directly the aldol condensation product rather than the aldol reaction product. So when the aldol product contains an aryl group at the beta position, dehydration occurs under the conditions in which the aldol addition will be carried out. So let's take this example. I have a ketone, it's an aromatic ketone. And when I do the aldol type of reaction in this, first I'll get the beta hydroxy ketone, and this will automatically get dehydrated, and we get the alpha beta unsaturated part here. That is because this double bond is in conjugation with the double bond of the ring. So that is an extended resonance here. So in such an event, we do not get this product. The product that we get is this one. All right. So let's look at the mechanism. How are these reactions happening? Let's see how it is happening here. Step 1, we have the aldehyde containing the alpha H. We have a dilute base, and we'll explain why we need a dilute base. The dilute base takes up the proton from the alpha carbon, one of the protons here. Water is removed, and we get a carbon anion. Now these hydrogens, the alpha hydrogens of aldehydes and ketones, are weakly acidic. They're acidic because this carbon anion, the negative charge here, this can resonate with the double bond O, and we get a resonating structure like this. So the anion is resonance stabilized with a negative charge on O, and the net, the actual intermediate is going to be the hybrid of these two. So that makes the alpha hydrogens weakly acidic. Now in the second step, we have the carbon anion attacking another molecule of the aldehyde. So I'm showing the two carbon compounds with different colors to make us understand which part is the one in which the carbon anion is formed, and in which part the carbon anion is attacking. Now this carbon anion is going to attack the carbonyl carbon here. It's going to attack this. The pi bond is going to shift to O, and we are going to get a product of addition. These two get added. As you can see, this CH2 is attacking this carbon. This is that CH2, the blue CH2, the one that had the carbon 9 character in it, and this is the COH part. And this carbon is this the C and the H is CH. This becomes O negative. This is the methyl group here, and they are attached now. And this is the step 2. The step 3 is when water, which is a solvent, is going to give the proton to this O minus and give us the aldol reaction. Now, one important aspect of this reaction is we use dilute base, and this is very essential to understand why we use a dilute base and why we can't use a concentrated base. Now, the problem is uh, any good base is also capable of acting as a good nucleophile. So, good base is a good nucleophile, okay? Because a base and a nucleophile only differ in the fact that the base attacks an acidic H, whereas a nucleophile will attack a carbon, which is electrophilic. An electrophilic carbon is attacked by the nucleophile, and a proton is attacked by the same species, in which case we call it a base. So whenever something attacks an acidic H, it's a base. If it attacks any other atom other than H, we call it a nucleophile. Now, for the same reason that it can act as a good base, it can also function as a good nucleophile. So in general, good bases are good nucleophiles too. Now what happens is that the basic character is always much more stronger than the nucleophilic ability. That is because for a good base, attacking an acidic H is far more easier than attacking an electrophilic carbon, because electrophilic carbon is often hindered, whereas an acidic H is relatively less hindered because hydrogen itself is attached only to one atom. So it is easier to attack an acidic H than attack an electrophilic carbon. So under dilute conditions, its ability to act as a base is generally high, but the ability to act as a nucleophile is low. On increasing the concentration, the ability to act as a base more or less remains the same, doesn't increase that much because it's already pretty good. Whereas the ability to act as a nucleophile increases drastically because more collisions are now capable of occurring with the electrophilic carbon, and therefore more collisions would imply more successful collisions, and therefore the ability to act as a nucleophile increases on increasing concentration. So the purpose of using dilute base in this reaction is that we want the OH minus to act as a proton acceptor. We want it to remove the proton, so we keep a dilute amount, a low amount. Whereas if we take a concentrated amount, let's say more than 50% by mass, then its ability to act as a nucleophile increases and it attacks the carbonyl carbon rather than attacking the acidic H. And that would lead to what is known as a Cannizzaro reaction. So this reaction requires a dilute base because less the concentration of the base, more is its ability to act as a base than a nucleophile. And if we use concentrated base, then Cannizzaro reaction will start competing with Aldol reaction. And we'll do a video on Cannizzaro reaction later. Now, another important aspect that we need to understand is that why is it that it is the carbon which is attacking this carbon? Why not the O? Because if you remember, this one had two resonating structures. One in which the negative charge was on carbon and the other in which the negative charge was on O. And this is actually a more stable resonating structure. So more of the hybrid would be of this nature than of this nature. The reason you get a carbon attacking a carbon is because, remember, this oxygen is the one which is carrying greater negative charge. Now, whenever an atom carries a lot of negative charge, we call it a hard base. And especially if it is on an atom which is small atom. Smaller atoms are called hard base. Larger atoms are called soft base. So the negative on carbon, this is the soft base, and the minus on O is the hard base. Now, this carbon has a slight amount of positive charge, a delta positive charge, because of the inductive pulling of O as well as the resonance effect of this carbonyl compound. Because a carbonyl compound has a resonating structure like this. For these two reasons, this carbon is electrophilic. But as you can see, this carbon does not have a full-blown positive charge. It has only delta positive charge because the more contributing structure is this one. Whenever an atom has a small amount of positive charge, we call it a soft acid. If it has a great amount of positive charge, a large amount of positive charge, we call it a hard acid. Carbocations are hard acids because they have a full-blown positive charge in them. Whereas this kind of a carbonyl carbon is a soft acid. Now there is a theory which we'll discuss later on, which is called the soft acid soft base theory. According to this theory, a soft acid prefers to attack a soft base, whereas a hard acid prefers to attack a hard base. We will do a detail of this when we do the nucleophilic substitution. But for the time being, let us accept this fact that a soft acid prefers a soft base. Now, of the two, carbon and oxygen, the C minus is the soft acid. And a carbonyl compound, carbon is a soft, no, sorry, this is a soft base and this is a soft acid. Soft acid and this guy is soft base. So soft base and soft acid, they are more likely to attack each other than the other way around. And therefore it is for this reason that the carbon is the one which is attacking the carbonyl carbon and not the oxygen. So it is the carbon that attacks the carbonyl carbon and not oxygen. This is because a soft base prefers a soft acid. Now, this kind of an aldol reaction can even be catalyzed in the presence of an acid. This is even an acid catalyzed process. So let's see the mechanism for that. So mechanism here. Step one, we have the carbonyl compound. The lone pair is on oxygen. It attacks the proton of the acid. It becomes protonated. Resonance. You got a resonating structure. Loses an alpha H. In essence, it tautomerizes to give you the enol part. So in the presence of the acid, we are going to do the reaction through the enol. Now in step 2, this enol is going to attack another molecule of the aldehyde. As you can see, this resonance is taking place. The carbon is becoming negatively charged. It attacks this carbon. The pi bond shifts to O and we get a product like this. It's an intermediate. And this will transfer a proton. This H will go to this oxygen. We call it intramolecular proton exchange. The proton shifts and you get the aldol. Now, we can even do the aldol with two different carbonyl compounds. So if I have carbonyl compound A and carbonyl compound B, And assuming that both of them have alpha H, then I can get four different products. One product is aldol of A with A, aldol of B with B. Then we have two products of aldol of A and B, and in one of them the alpha H of A is lost, and the other the alpha H of B is lost. So when two different carbonyl compounds, both having alpha H, are used in aldol, we get four different products. The ones in which A combines with A and B combines with B, we call it self-aldol. And when A and B mix with each other, we call it cross-aldol. And even in cross-aldol, we're going to get two types of products. We can have the alpha H of, let's say, the red going on. If I assume that the alpha H of this molecule goes, this alpha H goes, then I'm going to get this product where the alpha H of the red aldehyde, the propanol, is lost. And we can even have the alpha H of acetaldehyde being lost, in which case we will get this product. Now, there are certain particular conditions in which we will be able to get one of these exclusively. Under certain conditions, a mixed aldol can lead primarily to one product. One of that is by using one of the aldehydes without the alpha H. If suppose I have aldehyde A and aldehyde B, I have alpha H only on A, but I don't have alpha H on B, then when I do the cross aldol, then I'm going to get the alpha H of A going and that carbon anion attacking the aldehyde B. And the converse is, the reverse is not possible because B does not have an alpha H. So when one of the carbonyl compound does not have an alpha hydrogen, it cannot form a carbon anion and the number of possible products reduces to 2. And out of these two, now since A has alpha H, B doesn't, A can even undergo self-aldol. So to prevent that from happening, I can take B in excess. If I take B in excess, then whatever carbon anion of A is produced, it has a higher probability of meeting B because B is in excess than meeting itself. So if I have a cross aldol like this, I have benzaldehyde doesn't have an alpha H. I have acetaldehyde, it has an alpha H. And if I take benzaldehyde in excess, then I'm going to get alpha H of acetaldehyde going and the carbon anion attacking the benzaldehyde part. So I'm going to get a product like this. All right. Now, in those reactions in which I have an aldehyde or a ketone, or an aldehyde and an aromatic carbonyl compound, in which one of them lacks an alpha hydrogen, and we do the cross aldol, something like this given reaction, we call it the Claisen-Schmidt condensation. So the reaction between an aldehyde ketone and an aromatic carbonyl compound lacking an alpha H is called a Claisen-Schmidt condensation. Now, if you have an aldehyde and a ketone both reacting, both having alpha H, the major product is formed where the alpha H of ketone is lost and that carbon anion attacks the aldehyde. So what I'm basically talking about is, suppose I have acetaldehyde and I have acetone. The major product is formed by the alpha H loss of the ketone and this carbon anion attacking the carbonyl carbon of the aldehyde rather than the other way around. That is because of the two steps of aldol reaction in which in the first step the proton is lost and the second step the carbon anion. You see, if you look at this one, the proton is lost in the first step. This is going to become the carbon anion like this, and this carbon anion is going to attack the carbonyl carbon of the aldehyde. This is step 2. Okay. Now we know that the aldehyde's alpha H is more acidic as well as the carbon is more electrophilic. But the rate determining step, the slow step of aldol reaction is this step. The step in which the carbon anion attacks the carbonyl carbon. So this is the rate determining step, and therefore this is the most important step here. And since the carbonyl carbon of the aldehyde is more electrophilic, the chance of it getting attacked is far more than the carbonyl carbon of ketone getting attacked. And therefore, the final product, the major product, is the one in which the alpha H of ketone is lost, and that carbon anion attacks the carbonyl carbon of the aldehyde. So when an aldehyde and ketone, both with alpha hydrogens, are reacted together in a cross aldol type reaction, the major product formed is the one in which the alpha hydrogen of the ketone is abstracted and the carbon anion formed from the ketone attacks the carbonyl carbon of the aldehyde. Now, another way of obtaining an exclusively single product is by making sure that all the alpha H of a particular aldehyde are lost. So we convert aldehyde A into a carbon anion completely and then react it with carbonyl compound B. Now OH minus is a weak base. So OH minus, when it is added to a carbonyl compound, it is not capable of abstracting all the alpha hydrogens of all the aldehydes. And if you use concentrated base, then it undergoes Cannizzaro. So we can't use a large amount of OH minus to ensure that all the aldehydes are able to form the carbon anion. But if you use a strong base instead, a strong base would be able to remove the alpha H almost from all the molecules of the aldehyde, and that would in a way convert an entire aldehyde into the carbon anion. So we can achieve this by using a strong base like LDA, lithium diisopropylamide. This is LDA, lithium diisopropyl. There are two isopropyl groups on the nitrogen, amide. For example, if I take a ketone and if I add LDA to this, entire ketone becomes carbon anion. Now I add the other carbonyl compound. In this case, I'm adding the aldehyde, and you get the aldol product here, exclusively a single product. Now, if suppose the same compound has two carbonyl groups, then we can even have what is called as the intramolecular reaction. When a compound has two carbonyl groups, it can undergo intramolecular aldol condensation in the presence of a dilute base. And in certain cases, the ring size also is very important. If it can form a 5 or a 6 membered ring, then definitely this reaction is going to be more than the intramolecular one. For example, let's look at this one. Now, as you can see, this is the aldehyde part. This is the ketone part. And we know that in an aldehyde and ketone situation, it is the alpha H of ketone that is lost and the aldehyde's carbonyl carbon is the one that is attacked. So there are two alpha carbons of the ketone. If I get the alpha H of this H getting this carbon getting lost, this carbon anion is going to attack like this, and I'm going to get 1, 2, 3, 4, a 5 membered ring. Whereas if suppose this alpha H is lost and this attacks this carbon, I get 1, 2, 3, 4, 5, 6, 7 membered ring. And we know that a 5 membered ring is far easily formed compared to a 7 membered ring because of the proximity of the atoms. So in this particular case, we're going to get a 5 membered ring. Aldol product. Thanks for watching.